In this problem, we'll try to demonstrate how to apply topological sorting on a graph. Topological sorting is applicable only on acyclic graphs. That is, the graphs which doesn't have any cycles in them. Also, we have to know one important aspect, that for any acyclic graph, definitely there will be at least one vertex with 0 in degree. So while calculating the topological order of the nodes of the graph, we will start with the nodes whose in-degree value is 0. One can say the topological sort of a directed graph is one in which if there is a path from V to W, that is vertex V to vertex W, V comes before W in the ordering. Topological sorting is very useful in many applications, such as planning and scheduling of buildings or any projects, etc. For that matter, it is useful very much in analyzing the course prerequisite system, in which order the user has to do the courses, etc. For example, let us consider some of the activities in constructing a house. We may have the following types of activities: making foundations, constructing walls, constructing roof, then installing plumbing, installing windows, then finally decorating the house. If we see, all these tasks can be represented in a graph fashion as shown in the slide. So the possible order of these activities can be: first we may go for foundations, then walls, then roof, then windows, plumbing, then decoration, etc. That is one order. We can go in a different way also. That is, we can go foundations, walls, windows, decorations. After that, roofs, and then plumbing. That is indicating that after constructing the walls, then only we have to have roof. Similarly, after having the walls, we have to have plumbing. But there is one more aspect you have to see. When do you decorate? After making the roof, the decoration. But before decorating, the roof has to be over. But when do you require roof? When can you do roof construction? Walls has to be completed. So like that, this type of ordering, all the possible sequence ordering is known as the topological order. Finding out these orders are very essential in the project planning systems. Similarly, we have another real life example. It may be possible that course A has to be completed to join in the course B, which is also prerequisite for both the courses C and E. Then our problem comes is in what sequence the courses has to be carried out by the student to meet the degree requirements. This also a problem considered to be requiring topological order of the events. That is courses. Here events are nothing but completing a particular course. Here also we require some ordering of the courses so as to complete the requirements of the degree. So we use courses as the nodes, and to join in this course B, course A is required to be completed. So there will be an edge from this node to that node, indicating that this after this the course B he will be required to complete. So this type of dependencies are shown with the edges. Then we are interested to find out to complete the total degree in what sequence he can approach. So that is achieved by applying the topological ordering of the courses. We'll explain in the next slides how the same thing can be carried out. How really we can find out topological order of nodes of a graph. To achieve this, we can apply or approach the following steps. First, we can find a node which doesn't have any successor. That is, the node should not have any edge ending at this node. That is, its degree value is 0. We remove that graph, that node from that graph, and also we remove all the edges leaving out from this node, that is emanating from this node. Now we add this node in the output list. Again we apply the same operation on the remaining graph. This we repeat till there are no more nodes left in the graph. So the resulting output list becomes the topological order of the graph. Well, before we really delve into the algorithm, some aspects has to be recalled. The precedence relation is transitive. Similarly, the edges 1 and 4 and 4, 6 together implies that is there is an edge between 1 to 4 and 4 to 6 indicates that not only task 1 has to be completed, then only task 4 will be completed, and also only after completing the task 4, task 6 is completed, but it indicates indirectly that task 6 can complete or can start only if the task 1 is completed. That is, rather I say task 1 must be done before task 6. This is one precedence relation has to be satisfied or inferred from these two edges. Any sequence that satisfies these precedence relationships is called as the topological order of that graph. We are aimed at finding out such a order of a acyclic graph. Now consider the following task graph. It is a acyclic graph, directed acyclic graph digraph. It is having 6 nodes totally. The connectivity edges are shown in the figure. For this graph, the possible topological orders, acceptable topological orders which maintains the precedence relationship are 1, 2, 3, 4, 5, 6, 1 3 2 4 5 6, 2 1 5 3 4 6, 2 5 1 3 4 6. These are all possible topological orderings of the graph. Of course, to find out all these possible topological orders, we may require to find out or use some greedy algorithms. So that's the above graph. The topological order of the above graph can be 1, 2, 3, 4, 5, 6 or some other combinations as shown, indicating that task 2 or activity 2 has to be completed only after completing the task 1. Similarly, other precedence relationships has to be satisfied. Any relation satisfying this precedence relationship is called as, or any order which satisfies this precedence relationship is called as topological order. For one DAG, that is directed acyclic graph, there can be more than one topological order. It is acceptable. So next slides will demonstrate how the topological order can be calculated. While applying topological sorting on a DAG, the following points has to be remembered. The integrity of a vertex is the number of incoming edges. First, we select a vertex whose integrity value is 0 and we remove that vertex from the graph along with its edges, and at the same time we lower the integers of all vertices which are adjacent to this node. If there are several vertices having integrity value 0, we can select any one of them at a time. Each time we take one vertex whose integrity value is 0, we print the same thing in the output list, or we push into the output list, and then all its adjacent nodes integers will be adjusted. This is repeated till no more vertices are there in the graph. The following example will demonstrate the same. The graph is as shown in the slide. We may find that the node V2, that is the vertex V2, is the one which doesn't have any integrity. Rather, I say no edges are ending at that node. That is, its integrity value is 0. We select that one. We consider that is being outputted into output list, and all the edges which are leaving out from this V2, they are removed, and accordingly the integers of the adjacent nodes or vertices of this V2 will be reduced. If you verify, V0 integrity is 1. Now after removing V2, its value, integrity value became 0. Similarly, V5 integrity is 3. Once we remove V2, it will come down to 2. Like this, we adjust the integers of the adjacent nodes. Now, if we verify the remaining graph, the vertex V0 is the one having integrity value as 0. We select that one. At the same time, we remove the edges leaving out from the V0. Thus, the modified graph will be shown in the figure. At the same time, its adjacent vertices integers are being adjusted. Now, the node V1 is selected as its integer value is 0. Accordingly, its adjacent vertices integers are adjusted. Now V3 is selected as its integer value is 0, and similarly its adjacent vertices integers are adjusted. Now the node V4 is selected as its integer value is 0, and accordingly its adjacent vertex integers are adjusted. Now V6 is selected as its integer value is 0, and its adjacent vertexes integer values are adjusted. Finally, V5 is also selected. Its integer value is 0. Like this, the nodes first V2, then V0, V1, V3, etc. the nodes are printed as an output. That is the topological order of this graph. For this graph, the topological order is A, B, F, C, D, E. For this graph, A, B, E, C, D, F is not the acceptable topological order, as it is expected that all the arrows supposed to go to the right. Let us apply the topological sorting algorithm for this graph. Already we understood that first we are supposed to find out the vertices whose integer is 0. That is, the vertices which doesn't have any incoming edge. In this graph, we have two such a vertices. They are A, F. We can select any one of them, but however, we are going to select the A vertex. That will be kept in the output list. Also, we have removed all the edges which are going out from this node A. Thus, the modified graph becomes as shown in the slide. Again, we are supposed to find out those vertices whose integer is 0. That is, who doesn't have any incoming edge. Now, currently, B and F are such a type of vertices. We can select any one of them. We are going to select F. Thus, F will be kept in the output list. However, as F doesn't have any outgoing edge, graph structure will not change much. Again, we have to select the vertex whose integer is 0. That is, which doesn't have any incoming edges. Incidentally, B is such a vertex. So that will be selected. It will be kept in the output list. And then all the outgoing edges from this B will be removed. Again, we have to select the vertex which doesn't have any incoming edge. Incidentally, C is such a vertex. The same will be selected. It will be kept in the output list. And then all the outgoing edges from this node or vertex will be removed. Again, we have to select the vertex whose integer is 0. Incidentally, D is such a vertex. So that and kept in the output list, and all the outgoing edges from this D will be removed. Finally, the vertex E will be selected, and the same will be kept in the output list. Thus, the topological order of this graph is A, F, B, C, D, E. Evidently, the topological sorting algorithm involves three important activities. That is, to find vertices with no predecessors. That is, vertices with incoming edges 0 or in degree value is 0. And then we have to remove the outgoing edges from this node. And then we have to place this new node, selected node, into the output list. These are the main activities involved in this topological sorting algorithm. Before we discuss about what is the computational cost of identifying the nodes which doesn't have incoming edges, we shall discuss about the cost required to remove the edges. So we can see that removing is not so much of computational efforts are required. Its complexity can be said as order of E, where E is the number of edges in the total graph. So that is that many. Just removal means those there are totally E nodes, edges are there. So removing E requires only efforts in the proportional to E only. That its cost will be said as order of E. Similarly, placing the selected vertices in the output list requires the time proportional to V. Thus, the cost will be order of V. Now, the question comes is, what is the cost of finding out the vertices which doesn't have any predecessors? That is, which doesn't have any incoming edge or whose in degree value is 0. We would like to answer this question, assuming that the graph is stored or represented in adjacency list fashion. I'm sure all of you knows what is meant by adjacency list. That is, we maintain all the neighbors of a node in a linked list fashion as shown in the figure. Let us assume that we will initialize and maintain for each vertex its number of predecessors in the nodes of each vertex. For example, if you see the figure, we have A, number of predecessors for A is 0, for B 1, C 1, D 2, E 2, F 0. This is maintained in the linked list. Each time we have to traverse the adjacency list and find out the vertices with the in degree value as 0. Thus, we require the efforts proportional to number of vertices V. However, this we have to repeat for each node. Thus, the computational efforts required will be proportional to V square. Thus, in summary, if the graph is represented in adjacency list fashion, we require the time in the order of V square to find out the predecessors, and then we require order of E computations to remove edges, and order of V to push the vertices into the output list. The order of complexity of this algorithm can be said as order of V square plus E. Of course, you may be wondering, it is too costly. This algorithm is too costly algorithm. we need faster way to find out the predecessors which doesn't have any incoming edges. Let us assume either a queue or a stack which maintains vertices whose predecessor values as zeros. For example, in this example, we assume that there are some pointers in the queue which points to A and F whose predecessor values are zeros. When a vertex is removed, update the predecessor counts of all the adjacent nodes of this such that they will be reduced by 1. And if any such a any node's predecessor count becomes 0, push that node into queue. Let's assume that we are planning to remove the node A. If we remove A, we have to update the predecessor counts of its adjacent nodes. They are B and D. Currently, B value, predecessor count value is 1, so that will be reduced by 1. Thus, B value becomes 0. Thus, B will be pushed into the queue. However, D count will not become 0. Thus, it will be not pushed into the queue. Like this, when we remove a vertex, we check up the its adjacents, and rather I say we reduce its adjacents predecessor count values by 1. And if the predecessor count value becomes 0, that node will be pushed into the queue. Like this, the operation can be performed. Now F is removed. However, F doesn't have any adjacents, so now updating takes place. Let us assume that now B is removed from the queue. At the same time, its adjacents C, its predecessor count value will be reduced by 1. As it becomes 0, it will be pushed into the queue. Now C is in the queue. Now, when you remove C, its adjacents D and E, their predecessor counts will be reduced by 1. Currently, D's predecessor count is 1, thus it becomes 0. Thus, D will be moved into the queue. However, E predecessor count is 2, it will be reduced by 1, thus E predecessor count becomes 1. Now, D will be removed from the queue. Its adjacents, E is its adjacent. E's predecessor count is reduced by 1. Thus, E's predecessor count value becomes 0. Thus, E will be pushed into the queue, while D is moved into the output list. Now, E is removed from the queue, kept in the output list, and when we verify the adjacency list of the graph, E doesn't have any more nodes. Thus, the remaining nodes whose predecessor counts F will be simply printed. Complexity of this algorithm is of order V plus E, as the insertion and removal of the nodes vertexes into the queue requires only order of 1 time complexity. Thus, the total complexity of predecessor selection becomes only order of V. Thus, the computational complexity of this algorithm can be reduced like this. The following slides will explain how the same thing can be achieved, assuming that the graph information is maintained in a adjacency matrix fashion. First we'll read the adjacency matrix of the graph into a 2D array A. We select two 1D arrays known as INDEG and flag, and their values are initialized to zeros. And then by calculating the column sums of each column of the adjacency matrix, we calculate in degree of every node, and then we propose each time to select one node whose in degree value is 0 and flag value is 0. Once we find that a node whose in degree value is 0 and flag value is 0, we'll print its index value and we'll set its flag to 1. At the same time, we will traverse in that row of the adjacency matrix and find out the adjacents of this node and reduce their in degree values by ones. For the explanation purpose, we are taking the same graph of the previous example, having the nodes A, B, C, D, E, F. For our convenience sake, A means 0th node, B means node 1, etc. we are assuming. The adjacency matrix can be given as above. Now, by calculating the column sums of each column, we have calculated for each node in degree value. If we see the array in degree, we have 0, 1, 1, 2, 2, 0. So that is the in degree values of every node. Also, you can verify the flag array to be having zeros, indicating that the respective nodes are not yet printed or kept in the output list. Now we'll take the count value as 0. We'll start the while loop. Initially count value will be taken as 0. Then the while loop will try to find out the node whose in degree value is 0 and flag is 0. Incidentally, the first vertex itself having its in degree value as 0. Thus, its flag value we have made it as 1. And then by traversing that row, 0th row, because we are selecting the first node, that is 0, its index, we traverse the 0th row and identify its vertexes, adjacent nodes. So if you traverse the 0th node, you find 0, 1, 0, 1, 0, 0. It's indicating that the second node and the fourth node, they are the adjacents for this 0th node. So we will reduce their in degree values by 1. Thus, in degree value of second node becomes 0, and also in degree value of the fourth node, that becomes 1. Now again then we'll increment the count value by 1, and we have to traverse again to find out the node which or whose in degree value is 0. If you continue the while loop, now already one node we found whose in degree value is 0. Now another node we find that is the second node whose in degree value is 0. So that will be printed in the output list. that is second node, will be selected as the next node in the topological order. Its flag value will be made as 1. And now its adjacent nodes. How do we know? We traverse the adjacency matrix of row whose index is 1, that is second row. So if you verify in that row, third column value is 1, which means that third node is the adjacent for this B, or the second node. Thus, its integer value will be reduced by 1. Again, the counter value will be incremented by 1. As of now, 2 nodes are outputted into the output list. Now again, we traverse the array integrity. We find now third node, rather say index is 2, third node whose integer value is 0. So we set its flag value as 1 and we traverse that row, third row, and identify its adjacent nodes whose their integer values will be further reduced by 1. Again, counter value will be incremented by 1. Now again we traverse the array integrity. We found that fourth node integrity value is 1, 0. So that's its flag will be set to 1. And now we traverse the fourth row to find out its adjacent nodes. Their integer values will be reduced by 1s. Now if we continue this while loop, we may get other 2 nodes also in the output list. Like this, we can solve this problem of topological sorting with the help of adjacency matrix also.